Hello, and welcome to another brief video lesson on photometry, point spread function, or PSF. PSF stands for point spread function, which describes how an imaging system, a telescope, the CCD camera, image a singular point source, such as a star. When the CCD image, the object is divided into discrete point objects of varying intensity, with each object being computed as a sum of the PSF at each point. We'll explain. The PSF is typically determined entirely by the imaging system, and thus the entire image can be described by knowing the optical properties of the system. Understanding this, any CCD image can be studied through PSF applications. If we look here to the right, this is an image of a star zoomed in. What it's in essence showing here is something called the airy disk, which centrally has areas of light on the left and right side, but your principal star right here. We've seen this graph before when we talked about full width, half medium. So in a previous video lesson that we encourage you to review if you have questions on that particular topic. But you can see that these are all the same on a particular CCD image. So let's look at crowded field photometry. In very crowded fields, let's say a globular cluster or a dense star field, the star images become so close together that it's not possible to use aperture photometry with the sky annulus. There'd be too many stars. Let's review aperture photometry real quick. If you remember, we have three circles in aperture photometry. We have the target in the middle, we have a buffer zone, and then we have the sky background here. And sometimes you can have so many stars within this target zone that you can't get a small enough aperture to just look at the one target you want. Instead, there'd be too many stars compacted within there, and it makes your aperture reading using aperture photometry very difficult to do. The results of PSF is it gives you fewer stars to mess up the sky annulus by doing a subtractive method. In crowded field photometry with so many objects packed together, PSF is a leading solution. So let's look at two stars in an image. In any given image of the sky, stars appear to have different sizes. Bright stars are big, faint stars are small. This is actually a bit of an optical illusion. In a perfect optical system, telescope, CCD camera, and such, all stars across the entire image are actually the same size at the focal plane, that is, on the CCD chip. A closer examination of two bright stars on a particular image, when viewing their full width half maximum, shows almost identical in general shapes of the two profiles. And you can see that here. One star, but we have two stars in this measure corresponding to this image, and they're really the same on the focal plane of the CCD chip. The fainter star only appears smaller because there are fewer pixels above a given level than you have with a very bright star, such as the one on the right here. Therefore, every star can be considered a point source in itself, since it has a specific shape and size at the focal plane on the chip, and this is known as a point spread function, like this. So the PSF process. PSF should be circularly symmetric and can be plotted as flux versus the radius in a star image. So we have flux here, and then we have the radius coming out from the center. Full width half maximum helps us determine that. The angular size can then be characterized by the full width half maximum, which is the diameter where the flux falls to half its central value. So you can look at this here. We have the maximum, we have the basic sky background here, and this is the full width half maximum point. So in this case, we've got two stars of identical shape on the focal plane, here and here. And they're separated in a decent fashion right here that might be okay for aperture photometry. But as stars get closer and closer together, as you see in these images here, what happens is the two PSFs, point spread functions, or those shapes that we see characteristic here, begin to blend together. The black line then shows the resultant light output and how that changes. So if you take the image on the far right here, we basically have an outline that looks like one star, but it's a combination of two. So what PSF would seek to do in this particular case down here is to go, I know the shape of an individual star for each one of these images. If I subtract out one of those, just doing the math through the software program, I'll be left with just the light from the secondary. So if we knew the shape of this primary, you can subtract that and be left with just the light output from the secondary. Maybe that was the particular target that you wanted to study. So in a crowded field such as this, that is how you can employ this process to get an aperture in aperture photometry around that particular star and measure it. That's what the benefit of PSF does. So PSF modeling, advantages and disadvantages. Again, it's a model because it takes that particular shape and it applies it and subtracts it time over time from an image until it starts reducing and separating out those star values. So the stellar profile mode, you have to develop one, needs to come from the best, most illuminated, isolated stars in the chip, because your software has to understand what that point spread function looks like for your optical imaging system before it can do any subtractions. Multiple stars to reduce noise should be measured and be well spread throughout the frame. The advantages is you can do photometry work in crowded fields, globular clusters, tight star clusters, towards the center of the Milky Way, and so on. Areas in the image with the best signal noise ratio will determine the best PSF fit, and the background is actually included as a parameter. You know this from your review of aperture photometry. The background is a parameter, and we can use that to our advantage by subtracting it. A disadvantage is the point spread function. This modeling here does not perfectly fit all profiles. It's a good estimation. It varies across the CCD chip. You've seen in the cases of vignetting, when we've looked at bad image examples, that you could have a bright region in front, but you can have a curving or a falling off of light on the perimeter of an image. That's possible on a CCD chip. They're all different. PSF can be affected by seeing, which is the smearing of a perfect optical image due to turbulence or temperature differences. So there are advantages and disadvantages that have to be considered. Note, though, the disadvantages can be mitigated by analyzing multiple PSF models and would have an interpolation. So in summary, PSF uses known optical behaviors of both stellar light and your imaging system to decrease the complexity of an image and create separation between objects where there wasn't a separation before. The technique is beneficial when studying closely spaced double stars, stars in globular clusters, and stars in high dense areas. But note, PSF is not perfect. It depends on good models, low impact from atmospheric seeing, and a flattened CCD chip, meaning the response for your entire CCD image is fairly linear. Thank you for your time, and we look forward to seeing you in future brief video lessons.